Okay, here's 5.1b, concurrent lines, medians, and altitudes. Concurrent, that is where three or more lines intersect at exactly one point. Okay, let's take a zoom in over here. These lines all intersect at this point O, making these three lines concurrent right there at O. And so that point O would actually be considered the point of concurrency. So this is the point at which three or more lines intersect. Okay, and then we're just going to go through a couple of these theorems and let you know what these things are called. Perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. This point is called the, I'm going to write it below, it's called the circumcenter. And there you go. Okay. And the bisectors of the angles of a triangle are concurrent at a point equidistant from the sides, and this point is called the incenter. And you don't really need to know this, but the incenter and the circumcenter, they're actually centers of circles. One that the circumcenter is the center of a circle that circumscribes the triangle, and the incenter is the center of a circle that inscribes the triangle. So kind of neat. You could Google that, look at some pictures. And I showed the class that on GeoGebra. Pretty cool. Alright, this stuff in the box here. This is stuff that is going to be on your homework and is going to be on tests and quizzes. So if you weren't paying attention, you may want to start paying attention now. Alright, let me zoom in so I can write this right. Median of a triangle. This is a segment. Extending from the vertex to the midpoint of the opposite side. Okay. So a segment extending from the vertex to the midpoint of the opposite side. And if you look over here, we have some pictures of that. See here, you could see here's one vertex, and we have a segment that goes from point A to D, and D is in the midpoint of this triangle. Here we have a few more. A to D, you can see B going to E there, C going to F. So yeah, you got lots of examples of medians there. Now the medians, these guys are of course concurrent at a point, but what's really interesting is that they're concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So what we're saying here is you got all of these medians going together. Well, no matter what the shape of the triangle, if you were to go from C to G, that would exactly be 2/3 the distance of C to F, or BG would be 2/3 the distance of BE. So what if I was to tell you that this distance AD was a total of 21? Could you find AG and could you find GD? Well, if this total distance is 21, then that means you could divide into thirds. 21 divided by 3 is 7. So that means this distance here would be 7, and this distance here would be 14, making 14 plus 7, 21. We'll do some more problems like that, but I just want to explain that to you first. And this point, where all of these medians meet up, is called the centroid. Now, what's really unique about the centroid is it's the exact center of gravity of a triangle. So if you were to have some flat sheet that was a triangle, and you were to find the centroid, find all the medians, find the point where they all intersect, the centroid would be a point where you could have it balance, like right on your finger. If you put your finger right on the centroid, that triangle should balance right there at that point. It's the exact center of gravity. So it's kind of neat. But let's put into practice what we learned about that 2/3 thing now. So if the distance of FG is 5, so here's FG, it's 5. What is the distance of GC? Well, okay, it's important that since we know this is 1/3 the total distance and this is 2/3 the total distance, we could also say that this distance 1/3 is exactly half of this distance GC, right? Because if you're thinking about it, 1/3 that is exactly half of 2/3, right? So you can multiply these together, you cancel out, so 1/3 equals 1/3, right? So that's why that works. That's just a little arithmetic to show you why, but yeah, that's exactly going to, that little distance FG is going to be exactly half of this distance GC. So what is 5 half of? Well, 5 is half of 10, so GC has to be 10. Now another way you could have done that, maybe a little bit longer, but still just as good, is you could have said, well, I know that FG is going to be 1/3 of the total distance. So you could have wrote a little formula. You could have said, hey, 1/3 times x equals 5, where x represents the total distance, so FC. And then you would have solved for x. You could have multiplied both sides by 3, right? And then you could have said, oh, look, 3 and 1/3, they cancel out, so I get x equals 15. And then you would say, okay, if this total distance is 15 and this distance is 5, then I just need to do 15 minus 5. And you would get 10. So a few different ways, and there's probably a few more if you guys want to try and think of some other ways. I encourage you to. But what if the problem looks a little bit different? Okay, what if the problem looks like this one right here? It says if the distance of G is x plus 2 and the distance of B is 21, find x. Okay, now they're saying G here is x plus 2 and this total distance is 21. Well, and again, there's probably more than one way to do this, but I know that 21 divides pretty nicely when talking about thirds, right? So I could say 21 divided into thirds. Right away I got 7. So I know that this little segment right here has to be 7. So instead of doing much more work, I'm just going to say, hey, x plus 2 equals 7. And I can just do mental math and say, well then, x equals 5. So there you go. But now I want to zoom in and give you another type of problem that you might see. Okay, so let's zoom in, take a look at this. Now let's say that they would give you, I'm just going to make up some values here, but let's say from A to G, so I'm just going to kind of do this. They said that was, I don't know, 3x plus 5. Okay, and then they said G to D, that was, I don't know, we'll say 4x minus 8. Okay. Well, we said earlier, and I'm probably going to end up with a weird number here, but that's okay to prove my point. We said that GD, right, this distance is 1/3 of the total distance, and this is 2/3 the total distance, and 1/3 is exactly half of 2/3. So what we can do to set up this equation is we could say, hey, I know that 4x minus 8 doesn't equal 3x plus 5, but it does equal half of 3x plus 5. Or if I was to double 4x minus 8, then it would equal 3x plus 5. So here's how you would set up an equation like this. You could say 2 times 4x minus 8 equals 3x plus 5. And now I've doubled this distance here by putting that 2 in front, making it equal to that distance up there. And then you could just do the algebra and solve that problem. I'm not going to do it all for you guys, but you could kind of see how that would work. So lots of different ways to solve problems like this. And as long as you understand the concept that they equal, one of the distances is 1/3, the smaller distance is 1/3, and the bigger distance is 2/3, I think that you should be able to solve those problems. Okay. Altitude. Now this is a word you've probably heard before, but or a term you heard before, but you usually will call it the height. That's probably more often how you've heard of this part of a triangle, the height of a triangle. Well, that's the distance that connects to one vertice and is perpendicular to the line containing the opposite side. So, in the definition, we would say the perpendicular segment from a vertex to the line containing the opposite side. Now, the reason why they say line containing the opposite side, let me go over here a little bit and just show you something. Let's say I had some weird funky triangle like this. Okay, and then let's throw up a green line. If I wanted to be perpendicular to this triangle, there's no way that I could get it to connect to this opposite vertice. So what we do instead is we kind of imagine that this line gets extended, and then now we have a line that is perpendicular to the line that contains the opposite side and still hits this vertice. So our heights can actually be outside the triangle altogether. Okay, that's what we mean by the line containing the opposite side. Okay, so let's go back over here. The lines that contain the altitudes of a triangle are concurrent, of course. So here's an example of that. I'll zoom in. Right here, we got a whole bunch of lines meeting up. All these lines are perpendicular to the opposite side, and they meet up right there. And again, they don't have to meet up inside the triangle. In fact, anytime the triangle is obtuse, they'll meet up outside. Okay, and if the triangle is right, they'll meet up right in where they'll meet up wherever that right angle is. Okay, so let's go ahead and finish these notes real quick. The lines containing the altitudes of a triangle are concurrent. The point at which the lines containing the altitudes of a triangle are concurrent is called the orthocenter. Okay. Alright, so we have one last problem here, and if you haven't yet